Welcome back to Unit 2.4 Alkenes, and in this video we're going to start to look at the reaction of alkenes. So we're starting on page 11 and we're going to look first of all at the combustion of alkenes. And what we need to remember is that alkenes are hydrocarbons, so they consist of hydrogen and carbon only. And so when we burn them, they react with oxygen and they produce carbon dioxide and water if we have a plentiful supply of oxygen. That's because when carbon burns, it gives carbon dioxide, and when hydrogen burns, it gives water. If we have a limited supply of oxygen, like we met with alkenes, then it will produce carbon monoxide, but still water from the hydrogen burning, essentially. So just be careful, as we talked about and spent a bit more time with in alkenes. Read the question carefully. Is it a limited supply of oxygen or is it excess oxygen? So here we've got the example of propane reacting with oxygen. First of all, with an excess supply of oxygen. So again, decide your products first of all. So this is excess oxygen, so therefore we're going to get carbon dioxide and water. Then you need to balance, and again, my advice with balancing is do your carbon, then your hydrogen, then balance your oxygen last. I think that's the easiest way to do it. So we're going to need 3 carbon dioxides to balance the carbons. We're going to need 3 waters to balance the hydrogens, and then count up your oxygens on the right hand side. We have 3 times by 2, which is 6, plus these 3, which is 9. So you can write 9 over 2 in front of your oxygen, or multiply everything by 2. That would give you 2C3H6 plus 9O2, giving you 6CO2 plus 6H2O. However, if you had a limited supply of oxygen, then your products will be different. So we would get carbon monoxide produced and water, and then just balance from there. So starting with your carbon again, we'll need 3 carbon monoxides and we'll need 3 waters. Then count up your oxygens on the right hand side. We have 3 plus 3, which is 6, and so therefore we'll need 3O2. So with those type of questions, you may be asked to write the equation for the combustion of any alkene. Just check your products depending on whether it's excess or limited oxygen, and then balance. And then just briefly to talk about your observations with that reaction. Alkenes will burn with a slightly more orange and smoky flame, and it'll be slightly brighter and more luminous. And that's because they have a higher ratio of carbon to hydrogen in an alkene. It's only a slight difference, but because it will have a higher carbon content, that's what makes the flame more orange and more smoky. So if we were to take the example of propane versus propane, the formula difference is, with propane we have C3H6 following that general formula of CnH2n, and propane will be C3H8 because it has just single bonds, so you have 2 extra hydrogens following that general formula CnH2n plus 2. So you can see even from the ratio within the formula that there's a higher carbon ratio essentially in propane than propane. But as this statement says here, the higher ratio of carbon to hydrogen in the alkene. If we were to actually calculate that for each of these molecules, carbon to hydrogen in propane is 3 to 6, which is the same as 1 to 2. In propane then, our carbon to hydrogen ratio is 3 to 8, and that would simplify down, if we divide it by 3, to 1 to 2.666, if we round that off to 2.7. So you can see that it's a higher ratio of carbon to hydrogen. So in propane, there's 1 carbon for every 2 hydrogens, but in propane, there's only 1 carbon for every 2.7 hydrogens on average. So that higher ratio of carbon to hydrogen gives it a more orange, smoky flame than alkenes. So the next type of reaction that we're going to look at of alkenes are addition reactions, and these reactions we're going to spend quite a bit of time on. I'm going to talk you through, first of all, why these type of reactions happen, and then have a little look at some examples of these reactions. And you do need to be able to draw the mechanism of these reactions. Again, You're not going to be tested on these at this stage, but what we want to do with this is just introduce you to this type of reaction, introduce you to this type of mechanism, because there will be similar mechanisms that will come up at A2. So it's good if you have a good understanding of how to write mechanisms. And this will be more applicable than the one we saw with alkanes, that homolytic fission in the photochemical substitution of alkanes. So this reaction that we'll look at now with alkanes is a little bit more common. You'll see more similarity with in terms of reactions then that you'll study at A2. So as I say, I'm going to start off by talking you through, well, why do these reactions happen? And I think it's good to talk through this, good to understand this, because I think it then makes understanding the reaction and its mechanism that bit easier. So what we want to look at first of all is the double bond, and it's the double bond that actually causes these reactions to happen. It's the reason why these reactions happen with alkenes, but not with alkenes. And so we need to have a little look at the type of bonding within the double bond. And the double bond in alkenes consists of a sigma covalent bond and a pi covalent bond, and you can see their little Greek symbols in brackets there as well. How the double bond is formed is from the overlap of two half-filled orbitals from each carbon atom, and the way in which the orbitals overlap defines a type of covalent bond, so whether it's sigma covalent bond or a pi covalent bond. So let's have a look first of all at the electronic structure of each of these carbon atoms. So carbon has 6 electrons. So if I was to ask you to write the electronic structure, the electronic configuration of carbon, you'd probably write 1s2, 2s2, 2p6. So if we were to draw the electron in shells notation for that, it would be this, but don't write this in yet because we're going to actually change it. That would be 2 electrons in your 1s orbital, 2 electrons in your 2s orbital, and then 2 electrons in your 2p orbital, and that would be 1 in the 2px and 1 in the 2py, because remember those individual orbitals fill up singly first and then they pair up. But if this was the way carbon was to stay, then it wouldn't have enough unpaired electrons to form 4 bonds. We know that carbon forms 4 bonds. At the minute, it can only form 2 bonds with these 2 unpaired electrons, and because it forms covalent bonds, it needs to share its electron with whatever it bonds with and allow the other atom that it's bonding with to share one of its electrons to form that covalent bond. So what actually happens is that carbon will essentially promote an electron up from the 2s orbital into the 2p orbital. So that moves up here. Now you can see that there is 1 electron in the 2s orbital and then 1 electron in each of the 2p orbitals, so in the 2px, the 2py and the 2pz. And now you have 4 unpaired electrons ready to form bonds. You don't need to be able to explain that in an exam, but that's just where the 4 bonds that carbon forms arises from. So because carbon promotes an electron up into the 2p orbital from the 2s orbital, then this is the new electronic configuration. Again, you don't need to be able to write that, but for the next little bit, it's important that you understand that. And then just a reminder from your atomic structure topic what these orbitals actually look like in terms of their shape. So an s orbital is a spherical shape, the p orbitals are dumbbell shaped, and you've essentially the px, py and pz are all perpendicular to each other, all at 90 degrees to each other. Almost imagine an x, y and z axis, so one going across, one going up and down, and one coming out of the page essentially. And so we have got essentially 1 electron in each of these orbitals in the second energy level, so in 2s and 2p. So we have 1 electron in each of these, and essentially how these orbitals overlap will determine the type of bonding, so whether it's going to be a sigma covalent bond or a pi covalent bond. So far, just think 1 electron in each of the s and the 3p orbitals, so that's a total of 4 unpaired electrons And let's have a look now at how these can overlap. So over on page 12, we're going to have a look at how these orbitals from two different carbon atoms could overlap. So we're imagining two carbon atoms together, because remember what we're trying to talk about is the double bond in an alkene. So in other words, the carbon-carbon double bond. And there are a total of 4 ways in which the s and p orbitals can overlap. And essentially the overriding rule is, if you have direct overlap of orbitals, no matter whether they're s orbitals or p orbitals, then that is called a sigma bond. And that's a little Greek symbol there. It's like an O with a wee flick after it. And then we have indirect overlap. And that leads to a pi bond. Because when orbitals overlap, they can share the electrons that are in the orbitals and hence form a covalent bond. And the type of covalent bond, whether it's a sigma covalent bond or a pi covalent bond, will depend on whether you have direct overlap of the orbitals or indirect overlap. So let's have a look quickly at the 4 combinations. You don't need to worry about this too much, just essentially know what type of bonding is in that carbon-carbon double bond, but this just explains how it arises. So the first combination we could have is an s orbital from one carbon atom overlapping with an s orbital from another carbon atom. So think about that 2s orbital that has 1 electron in it for each carbon atom. And we could have essentially a 2s orbital overlapping with a 2s orbital from another carbon atom. If they overlap, because of their shape, because they're spherical, they're always going to have essentially direct overlapping. And that therefore is a sigma bond. So this is direct overlap, and you can see that happening there. You can see the 2s orbitals. On the left, they're not overlapping. On the right, they are overlapping. So this is referred to as a sigma bond due to the direct overlap of the orbitals. Second combination we could have is an s orbital from one carbon atom overlapping with a p orbital from another carbon atom. Again, you can see on the right here that that can be in direct overlap, again because of the shape of the s orbital. Anything essentially that involves an s orbital will be direct overlap. And so again, this is a sigma bond. The third combination we could have is a p orbital overlapping with a p orbital in a direct overlap. So again, direct overlap, you can see that here, is a sigma bond because we have direct overlap. So you can see the kind of lobes of the dumbbell shapes overlapping directly. But the fourth and final overlap that we can have is a p orbital overlapping with a p orbital, but in such a way that it's indirect overlap. So you can see it here. Essentially, these p orbitals are parallel to each other. I probably see this best as the py orbitals, essentially the orbitals that run along the y-axis, such as we would be used to drawing it in maths or on a graph. So you can think of these as py orbitals, and rather than them overlapping directly, so in other words actually on top of each other and overlapping, they can overlap essentially sideways. And what that leads to is what we call a pi bond. A bond that arises due to shared electrons. So these orbitals will still be able to share the electron that's in them. Remember, so think of these as the py orbitals. These will have 1 electron each in them if we're referring to 2 carbon atoms bonding with each other. And they can still share the electrons, but it's done in a kind of sideways motion. And what we have, what we form is represented on the right here in this kind of overlap. Here you can see in this diagram, it's kind of like the electron clouds are sort of merging together in a sideways fashion. You don't need to highlight that, but just to show where I was talking about there. You can see in the middle, there's no electron density as such, and that's because of your central points of your p orbitals. But then it's like your lobes overlap sideways and start to share their electron density as such. So that indirect overlap is what we call a pi bond. So if we were to look at the bonding between the carbon atoms in ethene, remember ethene has the formula C2H4. So the bonding between the 2 carbon atoms of ethene consists of a sigma bond, and that's because of the direct overlap, and a pi bond, which exists because of indirect overlap. And that's shown in the diagram below. So if you can see here, we've drawn the two of the p orbitals for each carbon atom. So you can almost imagine these as the px and the py orbitals, because they essentially run along an x-axis and a y-axis. And so you'll have one bond, the sigma bond, forming from the direct overlap of these px orbitals, if that's the orientation you're looking at it in, along the x-axis. So these two orbitals will be able to overlap directly, and that causes the sigma bond that you can see in the diagram on the right. And the sigma bond is a lot stronger than the pi bond, because it's caused by the direct overlap of orbitals. So you can see there it's drawn as kind of a full bond. Then you've got these py orbitals as such, and they can overlap indirectly, as I've kind of shown here, and that leads, so they're overlapping sideways, and that leads ultimately to the pi bond, and you can see that represented in the diagram on the right, as at the top and the bottom, because both of the lobes of the p orbitals are overlapping. Now, you may say, okay, well, carbon has two other unpaired electrons, one in the 2s orbital and one in, say, the 2pz orbital. And what that does is it uses those other unpaired electrons to form the bonds with the hydrogens. So you can see those there. We're not going to look at those closely at the minute, but those will also be sigma bonds. They'll also be caused by the direct overlap of orbitals, so those will be sigma bonds with the hydrogen. So that's how carbon uses its 4 unpaired electrons to form a total of 4 bonds. 3 of them will be sigma bonds. If we look at the example of ethene, then those sigma bonds will be one between the 2 carbon atoms and then 2 others with hydrogen atoms. And then the pi bond is formed by the indirect overlap of your p orbitals between the carbon atoms. And then there's just a brief note below that, obviously, which makes sense, the double bond between your 2 carbon atoms is stronger than a single bond would be, and it is shorter, and that also contributes to the strength of it. And that makes sense. It's sharing 2 pairs of electrons versus just 1, and so it's a stronger bond, requires more energy to break. But what we see is that it's not as strong as twice a carbon single bond, carbon-carbon single bond, and it's also not an awful lot shorter than a carbon-carbon single bond. So you can see there in the table below the bond length and the bond enthalpy of each of our carbon-carbon single bonds and carbon-carbon double bond. So you can see a carbon-carbon single bond has a bond enthalpy of 346. If the double bond was twice as strong, the bond enthalpy would be 692, but you can see that it's just 611, so it's not as strong as 2 times a carbon-carbon single bond. And that's because, as I mentioned previously, the pi bond, which is essentially the additional bond, is not as strong as a sigma bond because it's formed as a result of indirect overlap of orbitals rather than the direct overlap. So now that we understand a bit more about the type of bonding in the carbon-carbon double bond, let's briefly talk about what actually happens when the double bond reacts. So essentially what happens is the electrons in the pi bond in ethene or any other alkene, the carbon-carbon double bond of the alkene, they're in a pi electron cloud, which is much more susceptible to attack than the electrons in the sigma bond. And what we mean by attack is just reaction with another molecule. The carbon-carbon double bond has what we call a high electron density. Let me show you what I mean by that. And briefly, I'm just going to draw this diagram up at the top. I know I have a bit more room than you have in your notes, but maybe put an arrow in beside that little table of the bond enthalpies, etc., wherever you can kind of squeeze this in. If we just look at ethene, what we have is a carbon-carbon double bond, and then those have sigma bonds to a total of 4 hydrogen atoms, 2 each. So if we think about the electrons that make up these bonds, each of the carbon-hydrogen bonds is just a single bond, so 1 shared pair of electrons. So we can draw those in there. And then the carbon-carbon double bond obviously has 2 electron pairs, so we can show that like this. One of those will be a sigma bond and one will be a pi bond. I'll just highlight one in pink for the sigma bond, along with all of these carbon-hydrogen bonds. And then one of those carbon bonds will be a pi bond. That is essentially the second of your double bond, and that's the one that is prone to attack. That's the one that is caused by the indirect overlap of p orbitals, so it's easier to break. So when alkenes react, the pi bond is broken and the electrons in the pi bond can form sigma bonds with other atoms or groups. And we'll see that in our mechanism. That will make more sense when we look at our mechanism. But essentially what we see happening is the sigma bond breaking. So that's the one from the indirect overlap, the weaker of the 2 bonds essentially. And then it will use the electrons from the pi bond to form sigma bonds with other atoms or groups. And what that means is that the main reaction of alkenes is something called electrophilic addition. So it's different from the reaction that we looked at with alkenes. That was a substitution reaction where one atom or group is substituted by another. But this is addition, so we're actually adding on atoms or groups of atoms. Electrophilic simply means a species that likes electrons as such. It's an electron-loving species or molecule. Electro means electrons, philic means to like or to love. Some of you study biology, you know that hydrophilic are things that like water. So electrophilic is something that's attracted to this region of high electron density. And in alkenes, that region of high electron density is the carbon-carbon double bond. We can see that in the example of ethane that we've drawn here. That's a region of high electron density because we've got 2 electron pairs there between just 2 atoms. So 2 electron pairs in the one area. And so you can see that's explained here. The main reaction of alkenes is electrophilic addition because of the extra electron density in a carbon-carbon double bond. So alkenes are attached by species which like electrons, and these species are called electrophiles. So they like electrons. Think about what electrons are. They're negatively charged particles. So things that are attracted to regions of high electron density, things that like electrons are electrophiles. And they're going to have a positive or partial positive charge. That word partial is mentioned twice there. You can score that out here. So they possess a positive or partial positive charge so that they're attracted to the electrons. And down below you have a couple of examples. So you have hydrogen halides. And if you think about hydrogen halides, that's hydrogen bonded with a halide ion, something like chloride, bromide, iodide. And that is a polar molecule. The halogen atom within that bond is more electronegative, and so this is a polar bond. And so the hydrogen end of this molecule will be attracted to our region of high electron density in the carbon-carbon double bond. So that's an electrophile because it contains a partial positive charge. Then you've got things like concentrated sulfuric acid, which has the formula H2SO4, but that will break down into hydrogen ions and sulfate ions, and again these hydrogen ions will be our electrophile because they contain a full positive charge and they will be again attracted to this region of high electron density in our carbon-carbon double bond where we have 2 electron pairs. So molecules like this can approach the carbon-carbon double bond and attack it as such, in other words react with it. And as we said previously, what will happen is the electrons from the pi bond will break and form sigma bonds with these electrophiles. So examples like hydrogen halides and concentrated sulfuric acid. And there are other molecules, those are just examples, but you're looking for molecules that have a positive or partial positive charge. So pause there and have a little read through your notes what we've covered so far and just make sure that you understand that. So the bonding within the double bond and how that leads to the type of reaction that we're going to see with alkenes and with these addition reactions. We'll take a break there and then in the next video we'll have a look actually at what the mechanism looks like for this type of reaction. So the steps by which this reaction proceeds. So check out the next video for that.